Hello everyone, welcome back to Clear Creek Solutions hydrology education videos. It's another video in the Hydrology 101 series. I think we're on video 14 by now, and in this one we're covering infiltration in this video, so we're going to learn all about the basics of infiltration when it comes to hydrology. If you haven't already, you should download our hydrology terms guide. It's a great cheat sheet for you to have if you want to ever look up certain hydrology terms, hydraulic terms, whether you're in the industry or you're just learning. It can be a great reference for you when it comes to learning some of these aspects, because there's a lot when it comes to hydrology. So that's for free. If you go to the description box down below, you should be able to find that guide, and you'll get 100% free. So let's start talking about infiltration. What is infiltration? So infiltration is the movement of water through the soil surface and then into the soil. So if you think about it, if we have some grass, just some regular grass, and it rains on it, the water's just not going to pool up on the surface and run off, right? That's what it does for impervious surfaces. But if you've noticed, if you've ever poured water on dirt or something like that, the water actually infiltrates through the soil particles because it's not 100% solid and impervious. There are gaps in that soil. So that's where the water is going to move through, because water is always going to use gravity to move to the lowest point. So this is what we refer to as infiltration. But what really matters is the kind of soil that the water is raining on, because it's going to infiltrate differently. The infiltration capacity of a soil at any time is the maximum rate at which water will enter the soil. Infiltration capacity depends on many factors. So the soil will only have a certain amount of capacity until it's completely saturated and the water will have to move on. And then the rate of that infiltration is what's referred to as the infiltration rate, which is used a lot in hydrology and design to determine the design aspects of certain facilities. A loose permeable soil will have a higher capacity than a tight clay soil. If much of the pore space is filled with water, infiltration capacity is generally less than when the soil is relatively dry. So let's talk about this. So if we have, and we're going to I'll show you a table here at the end of this lesson too, so you can help understand this. But if you think about some sand, right? The sand particles, have you ever done sieve analysis? The particles are very, very small. There's going to be lots of gaps between it. When you think about something like clay, where it's almost very solid when you see something like clay, when you were to dump a bucket of water on a patch of clay versus a bucket of water on some sand, the water is going to really infiltrate into that sand, but not as much through the clay because the particles are more closer together. It's going to rely on the pore space to determine how much water is able to infiltrate through that soil. And then, of course, the saturation of that soil before the water is rained on that soil will also determine how much infiltration can occur. So if your soil is already completely saturated, you're not going to get a lot of infiltration because it's already filled with water. There's not a lot of room for new water to move in. So if the pore space at the surface is completely filled with water, further downward movement of moisture is controlled by the subsoil permeability. So a permeability factor will be in place to determine how that water is going to move when it goes onto a completely saturated surface. A hard driving rain may pack surface dirt into soil pores and reduce infiltration. A good vegetal cover provides protection against raindrop impact. In addition, plant roots and organics, plant litter help to increase soil permeability. So actually, if it rains quite hard on a patch of soil, it's actually going to pack those particles together and over time reduce that infiltration, because we're losing more of those soil pores and those openings in the soil, reducing the infiltration. And in a lot of cases, we do want infiltration when it comes to stormwater modeling, because that means the water is able to naturally infiltrate into that soil and then get filtered out and mitigated back into the water cycle. It's when that water runs off in large volumes and over lots of different occurrences that we start to run into issues when we come into project development. If the infiltration capacity of a soil were known, the volume of runoff resulting from a given rainfall could be computed by subtracting infiltration and surface retention from total rainoff. So this is just saying here, if we know the infiltration capacity of a soil at a given time, and then the volume of runoff, we could determine how much of that was infiltrated and how much of that was retained by the soil. So the infiltration rate, which I talked about earlier, is the rate at which water actually enters the soil during a storm. It must equal the infiltration capacity or the rainfall rate, whichever is less. So the actual rate is the rate at which that water is going to enter the soil during any form of stormwater event. Infiltration rates or capacities are estimated experimentally by measuring the surface runoff from a small test plot subjected to either natural or artificial rain. So sort of as I discussed before, you're going to take a soil plot, you're going to dump some water on it and be able to measure how much that water was able to infiltrate, how much of that went into the system as runoff. Then we can determine the infiltration rate of that soil. If the plot is subjected to rainfall rates in excess of the infiltration capacity, the capacity will vary with time. Different capacity curves will be obtained for different values of initial soil moisture. So if we think about our curve, which I'll show you soon, and if it begins to rain on that curve early in the process, more and more of that soil is going to infiltrate because there's less of that water taking up the open pore space. But as we continue to pour water on it, more of that space is taken up, and we're going to get less and less infiltration over time, especially if the soil saturation was saturated before the stormwater event occurred. So here's an example of an infiltration curve here. We've got the rates and we got time. As you can see, we progress with time, the infiltration goes down less and less and less, because if we have a lot of rainfall, it's going to infiltrate a lot until it hits a certain peak, and then it's just going to go down. So you can see the infiltration capacity curve starting up really high and then going down as the precipitation rate begins to go up. So many thousands of infiltration tests have been conducted. Infiltramometers may consist of small plots of ground sprayed with water to simulate rainfall, or tubes partially embedded in the soil and then filled with water. These tests have indicated that the infiltration capacity of bare soil under average summer conditions and after 1 hour of rain will vary from 0.01 to 1 inches per hour, which is the common metric that we use for infiltration rate when you're using English units. So here's a picture of that. I think the infiltrometer over here, this is a double ring infiltrometer here, used to help measure the infiltration rate. And then here's a table of some of the textural classes of soil and the basic infiltration rate. This is in millimeters per hour. Most in English units are in inches per hour. You can convert it or just sort of see relatively what each of these do. As I discussed before, sand's going to have a lot of infiltration because of the pore space. If you go all the way down to clay, very little infiltration, 1 to 5 millimeters per hour. Sand having up to 30 inches per hour. It's really going to determine and be based off the soil type on your project site, which is very important when it comes to your stormwater design. So natural rain and varying intensities, sometimes below and sometimes above the prevailing infiltration capacity, results in distortion of the capacity time curve. The decrease in infiltration capacity during periods with rainfall rates less than capacity is not so great, as it's when infiltration takes place at capacity rate. And then it is often assumed that the infiltration capacity at any time is determined by the mass infiltration that has occurred up to that time. So that's a basic overview of infiltration. We're going to go more into it in depth in the next video. Make sure you download the hydrology terms cheat sheet, and we'll see you guys next time.